Welcome to this video on portfolio volatility. Portfolio volatility is used to measure the risk of financial portfolios. Here you can see the agenda of the video. After a motivation, I'm very shortly going to talk also about expected portfolio returns. That's fairly easy. And then we are going to focus on the main part of this video, portfolio volatility. Portfolio volatility is the standard deviation of portfolio returns. And you will learn that the correlation of portfolio returns of the different assets in a financial portfolio have a very large impact on portfolio volatility. I'm going to show you first how to calculate the portfolio volatility for portfolios consisting of two assets, and then we are going to look at how to calculate portfolio volatility for portfolios consisting of more than two assets. At the end of this video, I'm going to talk about alternative formulas to calculate the portfolio volatility. This is the motivation part, where I first define what a financial portfolio is. A portfolio is a collection of financial assets. I assume you know that already. We call these financial assets the portfolio constituents. Portfolio weights are the percentages that you invest into each of these constituents. And obviously, the sum of all portfolio weights must be equal to 100%. If we know the portfolio constituents, the portfolio weights, and the value of the portfolio, we have completely defined the portfolio. This is a short example on portfolio weights. Consider a financial portfolio that is invested into two stocks, in stock A and stock B. These two stocks are the portfolio constituents, and the market value of these investments are 200,000 and 300,000 euro respectively, so the portfolio value is 500,000. How can we calculate the portfolio weights? For asset A, we divide the value that is invested in stock A by the total portfolio value, and we receive a weight for asset A of 40%, and for stock B, the portfolio weight is 60%, and you can see that 40% plus 60% is equal to 100%. The sum of the weights must always be equal to 1. Diversification is a key concept in asset management. You've probably heard that saying, don't put all your eggs in one basket. This means you should not invest all your money in only one single asset, but rather you should invest into different assets, and this can reduce the risk of your portfolio. The strength of diversification is typically measured with a mathematical concept called correlation. The correlation of assets, which we denote with the Greek letter rho. The correlation can range from -1 to +1, respectively from -100% to +100%. You can see here 3 simulated scatter plots of asset returns. In each of these 3 plots, I have simulated the returns of 2 financial assets. In all 3 plots, the correlation is positive. This implies that there is a tendency that if one asset has high returns, that the other one has also high returns, and if on the other hand the one has very low returns, then there's a tendency that also the second asset has low returns. On the right hand side we see simulated returns with a correlation of 80% or 0.8, and you can see that here the correlation is very strong, and there's a very strong tendency that if the one asset has high returns, that also the other one has high returns. In contrast to this, on the left hand side you can see simulated returns of assets with a low positive correlation, and here the tendency is very weak. We can say that the lower the correlation is, the higher is the diversification. I have prepared this example to show you the effect of diversification, of investing into several assets rather than in only one asset. Consider the risk which we will measure as volatility or standard deviation of asset returns of an equally weighted portfolio that consists of different constituents. They all have the same risk and they have different correlations that we assume. In the one example, we assume correlations of 50% between each of the assets. In the second example, we consider a correlation of 30%, and we also look at what happens if there is a correlation of 0. Let's look at this bar chart here, and let us first consider the blue bars. They represent the diversification if the correlation between the assets is 50%. So if you invest in only one asset, this is our starting point, you have 100% of the risk. And now if you, instead of investing into only one asset, you invest in 10 assets, here you see you can reduce the risk by roughly 25%. If the correlation is only 30%, this is the red bar, you can reduce the risk by almost 40% if you invest in 10 assets rather than in only one asset. A correlation of 30% is realistic to find. Also 50%, you will find a lot of assets that have, or pairs of assets that have a correlation of 50%. It is probably very difficult to find assets with a lot of assets with a pairwise correlation of 0. But here, if you look at the gray bar, if you could find 10 assets with a correlation of 0, this would reduce the risk by roughly 70% if compared to an investment in only one asset. In this video, we assume that asset returns are normally distributed, which is also the assumption made in the so-called modern portfolio theory, started with Harry Markowitz's famous article Portfolio Selection in 1952. This is the basis for a lot of models that we have in finance, and Mr. Markowitz also received the Nobel Prize in Economics for his work. However, people have found that the risk could be underestimated if we assume normally distributed returns, which is specifically true for short time periods. So there exist advanced models at the moment. A lot of people like to model joint distributions with so-called copulas, which replace the concept of correlation, and they use volatility adjusted returns to calibrate their models. But these approaches go beyond the scope of this video. So in this video we will focus on normally distributed returns. Before talking about portfolio volatility, I shortly want to address also the expected portfolio returns. The expected return of a portfolio can be calculated very easily on the basis of the expected returns of each of its constituents and the portfolio weights. We then use the formula that you can see to calculate the expected return of the portfolio. So what we need to do is, for every constituent, we must multiply its weight with the expected return of the constituent, and then finally take the sum of these results. I've got a very simple example here. Consider this portfolio consisting of 3 stocks. You can see in the table the portfolio weights, 55%, 25% and 20%. The sum of the portfolio weights is equal to 100%. That's fine. And then you can see here the expected return, 4%, 6% and 7%. What we have to do is we have to multiply these two values, and these two values, and then take the sum of the results. So weight 1 times expected return 1, and so on and so on. You can see the expected portfolio return is 5.1%. For the example, I used Excel to calculate the expected return. You can see the same example here in this Excel sheet. Here the portfolio weights, the expected returns. What I've done, I've multiplied the weights with the expected return for each of the constituents, and then finally summed them up, and the result is an expected return of 5.1%. Let us now turn to portfolio volatility, and we start with the formulas to calculate portfolio volatility for portfolios that consist of 2 assets. You find displayed 2 formulas. They yield the same result, and when you have a closer look at the formulas, you will see that they are very similar. The highlighted area is the same in both formulas, and actually there's only a very small difference between the two formulas. In the first formula, we have here the covariance of returns between asset 1 and asset 2, whereas here we have this expression. The correlation times the standard deviation or volatility of the first asset multiplied with the volatility of the second asset. Typically, you will use the second formula because normally when we talk about stocks and their relations, we don't talk about covariances, we rather talk about correlations. You might remember that this is the formula to calculate the correlation when you know the covariance and the volatility of asset 1 and asset 2. So the correlation is always the covariance divided by the two respective sigmas. And if this holds, you know that you can express the covariance like this: correlation between asset 1 and 2 times the volatility of asset 1 times the volatility of asset 2. And this is what we have done here. We have written down the covariance in a different way. Let us apply the formulas that we have learned so far in this example. We have a portfolio that consists of two assets, asset 1 and asset 2. The portfolio weights are 60% and 40%. The expected returns are 5% and 7%. And the portfolio volatility is 10% and 15%. So we see we have invested a larger fraction in asset 1. Asset 1 has a lower expected return but also less risk, and asset 2 has a higher expected return but also more risk. The correlation between the returns is 30%. We now want to calculate first the expected return. The expected return is simply weight 1 multiplied with the expected return 1 plus weight 2 times the expected return 2. And we have an expected return of 5.8%. Now let's calculate the portfolio volatility. We use the second formula. What we have to find or calculate is weight 1 squared times sigma 1 squared plus weight 2 squared times sigma 2 squared plus 2 times weight 1 times weight 2 times correlation 1, 2 times sigma 1 times sigma 2, and then take the square root. We see the respective values in the table here. Weights, volatilities. First we have to square them, and then 2 times weight 1, weight 2, the correlation which we find here, sigma 1 and sigma 2. You see, the resulting volatility is 9.6%, a little bit less than 10%. What is striking in this example is that we have combined these two assets, and you see that asset 1 has a volatility of 10% Asset 2 has a volatility of 15%, but because of diversification effects, we receive a portfolio with a volatility of only 9.7% roughly, which is less than the 10% of asset 1 and definitely less than the 15% of asset 2. And at the same time, we have an expected return of 5.8%. So the expected return is higher than the expected return of asset 1, and the risk is lower than the risk of asset 1. Let us now have a look at the impact of different correlations on the portfolio volatility. We have the same example as before. Our portfolio consists of two assets, asset 1 with a lower expected return and a lower volatility, and asset 2 with a higher expected return, but asset 2 is also more risky. We have already calculated the expected return of the portfolio. Different correlations do not have any impact on the expected return of a portfolio, and here again you can see the formula to calculate the portfolio volatility. We now want to calculate the portfolio volatility for different scenarios concerning the correlation. So you find here 6 scenarios with different correlations. In scenario 1 we even have a slightly negative correlation. In scenario 2 the asset returns are uncorrelated. A slight, very low positive correlation. In scenario 4 and 5 comparably higher correlations, and finally in scenario 6 a perfect positive correlation. You might want to stop the video now and try to calculate the portfolio volatilities for the different scenarios. You can see here the portfolio volatilities for the different scenarios, and what you can see is that the lower is the correlation, the lower is the resulting portfolio volatility. Let us now look at the impact of different weights on the portfolio volatility. We still have the two assets as before, asset 1 which is less risky and asset 2 with a higher expected return which is more risky. And we want to combine these two portfolios, and I have calculated the expected return and volatility for portfolios for different portfolio weights and for 3 scenarios. The first scenario is a correlation of 30%, and the result, the risk-return combinations are displayed in the black line. The second scenario is a correlation of 50%. It is displayed by the red line, and also I have calculated the risk-return profiles for a correlation of 100%. I have used weights going from -150 to +150% for the respective assets. How can I interpret a weight that is negative? Well, this is a short position. So in one extreme case, you could have a position or a portfolio weight of minus 50% in asset 1, which would be a short position in asset 1, and a weight of 150 in asset 2, a long position. Obviously, the sum is 100%. And the idea is you borrow asset 1, sell it, and invest the proceeds into asset 2 together with your initial endowment. Hence, if asset 1, in this specific case where you have a short position, if the price would go up, you would lose money, and if the price goes down, you earn money. Let's have a closer look at the risk-return profiles. So let me repeat, the black line represents a correlation of the risk-return profiles if the correlation is 30%. The red line is the profile for a correlation of 50%, and the blue line is the risk-return profile for a correlation of 100%. Here you can see the standard deviation of asset 1. Let us zoom into the relevant area. So if I invest 100% in asset 1, I have an expected return of 5% and a volatility of 10%. If I invest 100% in asset 2, I have an expected return of 7% and a volatility of 15%. And what is interesting to see is what happens if we combine these two assets. Here we have short positions. We will not focus on the short positions here. Let us focus on the scenarios where we have long positions in both assets. Let us first have a look at the scenario, the black line, where the correlation is 30%. What you can see is that if instead of investing 100% in asset 1 and 0% in asset 2, if we reduce the portfolio weight of asset 1 a bit and add a bit of asset 2, we have a portfolio, a resulting portfolio, which has higher expected returns than asset 1, but less risk. If we intended to set the portfolio weights to arrive here, which means we have a large fraction invested into asset 1 and but less than 100%, and a certain positive portfolio weight for asset 2, we can have a portfolio that has the same risk as asset 1, but a higher expected return. So the black line is the 30%. The red line is the 50% correlation, and you see when we have 50% correlation, the effect is still here, only it's not as pronounced as in the scenario with the 30% correlation. What you can also see that if we assume a correlation of 100%, but this is an extreme case that we will not observe in the real world, then there is no diversification effect. then the risk is simply a linear combination of the individual risks of the two assets. What I have done now is I have calculated the minimum variance portfolios for the different correlation scenarios. What are minimum variance portfolios? Well, it is the combination between asset 1 and asset 2 that achieves the lowest possible portfolio volatility, the lowest risk. Let us first consider the example, the scenario with a correlation of 30%. So if we set the portfolio weights to 76.6% for asset 1 and to 23.4% for asset 2, we have an expected return of 5.47 and a portfolio volatility of 9.33. So this would be in this area here. We have a portfolio that has a higher expected return than asset 1, but a lower volatility. So it would not be wise to invest 100% in asset 1. It would be definitely better to invest, to combine asset 1 with asset 2 to receive portfolios with a higher expected return and less risk. For the scenario with 50% return correlation, we see that the minimum variance portfolio has an expected return of 5.29 and a volatility of 9.82%, and the respective portfolio weights are roughly 86 and roughly 14%. Let us now move from the two asset case to the more general case where we say we have a portfolio consisting of n assets, where n can be any positive integer number. Again, I have presented two formulas that yield the same result, and as before, you see that the only difference is that in the first formula we have the covariance, whereas in the second formula we have the covariance expressed by the correlation and the different volatilities of the constituents. I will address the mathematical notation a bit later. Rather, I want to give you or present to you now a cookbook recipe, how you can interpret these formulas, respectively, how you can calculate the portfolio volatility. So this is the cookbook recipe. We have two steps to calculate the portfolio volatility. The first step is to calculate the portfolio variance. So we do not have the square root here. And apart from that, it looks like the second formula that I've just presented to you. How can we do this? The first step is we look at this part of the formula. We simply add the products of the squared weights and the variances. So we interpret this as W1 squared times sigma 1 squared plus W2 squared times sigma 2 squared, and so on for all portfolio constituents. Then for step 1b, what we have to do is we have to find out all pairwise combinations of the assets in our portfolio, and for each of these combinations we calculate this product here. And then finally, step 2 is easy. We have calculated the portfolio variance, and then we take the square root from the variance to calculate the portfolio volatility. Let's try to apply this algorithm on a specific example. In this example, we have 3 assets. The first 2 assets we know already from the previous example, asset 1 and asset 2, and now we add a third asset, asset 3. Asset 3 has an expected return that is higher than those of asset 1 and asset 2, but asset 3 is also more risky with a volatility of 20%. Here you can see the pairwise correlations. So the correlation between asset 1 and asset 2 is 50%. Between asset 1 and asset 3 it's 30%, and between asset 2 and asset 3 it's 40%. For step 1a, we must now calculate for every constituents Wi squared times sigma I squared, and then add the results. So step 1a is calculated as W1 squared times sigma 1 squared plus W2 squared times sigma 2 squared plus W3 squared times sigma 3 squared. We can find the values here and simply add them or insert them, and the result for step 1a is 0.006125. For step 1b, we must now figure out the possible pairwise combinations of our 3 assets. What are the possible pairwise combinations? The first possible combination is the combination 1, 2. The second possible pairwise combination is the combination 1, 3. And finally, the last possible combination is the combination 2, 3. Okay, there are 3 possible pairwise combinations. Let's start with the first possible combination, 1, 2. We must calculate 2 times W1 times W2. We find these values here, times the correlation between 1 and 2, which you can find here. It is 0.5 times sigma 1 times sigma 2. And to this we add the product for the combination 1, 3, and then finally the product for the combination 2, 3. Now we insert the values and get a result for step 1b of 0.00489. If we add the results from step 1a and step 1b, we have the portfolio variance. And then step 2 is easy. We simply take the square root of the portfolio variance, and this is then the portfolio volatility, which is roughly 10.5%. If we now also consider the expected return of the specific portfolio, we see that the expected return is 6.2%, which is considerably more than the expected return of asset 1, but the portfolio volatility is only a bit higher than the volatility of asset 1. I have calculated the portfolio volatility for the example that we have just seen also in Excel. You can see here the portfolio weights, the expected returns, and the volatilities of the constituents. Here you can see a correlation matrix. How to interpret this? Correlation 1, 1 is 1. That's not relevant for us. The correlation between 1 and 2 is 0.5. The correlation between 1 and 3 is 0.3. And the correlation between 2 and 3 is 0.4. What you can see here is the so-called variance-covariance matrix, which we have not used in our example. Let me now address step 1a, where we had to calculate for every constituent wi squared times sigma I squared. I did this here for asset 1. This is the result for asset 2, W2 squared times sigma 2 squared, and here's the result for asset 3. And the result for step 1a is simply the sum of these three values. I now go to step 1b. Here we have the possible combinations. Combination 1, 2, 1, 3, and 2, 3. For each of these combinations, we had to calculate 2 times Wi times Wj times the correlation times sigma I and sigma j. Here you see the weights. Here you see the correlation. Here you can see the sigmas, the constituents, volatilities. And we must write 2 times. We do the same for the combination 1, 3 and for the combination 2, 3. Adding these 3 values gives me the result for step 1b. If I multiply the result from step 1a and step 1b, this is the portfolio variance. And finally, if I take the square root of the portfolio variance, I can see the portfolio volatility. I'm quite sure that you are aware that x to the power of 0.5 respectively to the power of 1/2 is the same like taking the square root. This is the way I prefer to write it in Excel or in programming languages. Let me repeat the results for our example. We have a portfolio consisting of 3 assets. Here are the portfolio weights. Here you find the expected returns of the assets and here their volatilities. This is the correlation matrix containing the pairwise combinations, the pairwise correlations of the combinations, and this is the expected return, 6.2%, the portfolio volatility, roughly 10.5%. We have just calculated it down here. I have calculated it here using a different formula. I will come back to this formula in a minute. And I have additionally calculated the Sharpe ratio. This is a risk-adjusted performance measure that sets the expected return in relation to the volatility. It is defined as the excess return over the risk-free rate divided by the volatility. If we assume that the risk-free rate is 0, then it's simply the expected return divided by the portfolio volatility. If you have prepared a sheet like this one, you can also do some optimization procedures. For example, we could try to find the minimum variance portfolio. For the minimum variance portfolio, we would minimize the volatility by changing the portfolio weights. I show you here one small trick that I always use. In the original example, weight 1 was 50%, weight 3 was 30%, and weight 2 was 30%, and weight 3 was 20%. But I define weight 3 as 1 minus the sum of weight 1 and weight 2, which helps me to make sure that the sum of the portfolio weights is always equal to 1. I will now use the Excel solver to find the minimum variance portfolio. I'm going to minimize the portfolio volatility. I'm going to minimize it by changing weight 1 and weight 2. And implicitly by changing weight 1 and weight 2, I also do change weight 3, but I can make sure that the sum of the weights is equal to 1. Let's solve this. Okay, we have found a portfolio with an expected return of 5.45% and a sigma volatility of only 9.7%. Again, a higher return, expected return than asset 1, but a lower volatility than asset 1. We could also try to find the so-called market portfolio. The market portfolio is the portfolio that maximizes the Sharpe ratio. So I want to maximize the Sharpe ratio again by changing weight 1 and weight 2, which implicitly changes weight 3. This is the result. Here you can find the respective weights. The expected return is a bit more than 6%, and the volatility is 10.2% roughly. I have displayed here the weights, expected returns, volatilities, and also the Sharpe ratios for the original example. Here you see the weights. These are the weights for the minimum variance portfolio, and here you can find the weights for the market portfolio. Consider now the case where we have 4 rather than 3 assets. We can still simply follow the algorithm. You remember step 1a, step 1b, and then step 2. And the only somewhat difficult task is to find out the possible combinations. So when we have 4 assets, there are 6 possible pairwise combinations. 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, and 3, 4. There is a helpful formula to find out how many pairwise combinations there are for n assets. The formula is displayed here: n times n minus 1 divided by 2. So if we have 5 assets, there are 10 possible combinations. For 20 assets, for example, if you want to calculate the volatility of the ATX on the basis of its 20 constituents, you already have 190 combinations. And consider the case of the S&P 500 consisting of 500 stocks. Here you have 124,750 possible combinations. Having presented to you a cookbook recipe how to calculate the portfolio variance, respectively volatility, I now want to devote the next few minutes on the interpretation of the mathematical notation that is somewhat complicated. Here you find the formula for the portfolio variance, sigma squared, in order to calculate. So this would be step 1 of the algorithm. In step 2, we then would take the square root of this to arrive at the portfolio volatility. The first part is easy to interpret. So it's for all constituents wi squared times sigma I squared, and then the sum of these products. This is easy to interpret for most people. So in the case where n is equal to 3, we have the formula for this expression written here. The second part of the expression is a little bit more difficult to interpret. It's 2 times, actually I always put the 2 in here, but it's a question of taste. I don't like to have so many brackets, so you can take the 2 also inside here, and you will understand that this is the same thing. we go for I from 1 to n, and for j also from 1 to n, but we add this term here only if j is larger than I. So let us start this procedure now. We start with I is equal to 1 and j is equal to 1. And we would enter this, write down this term, but only if j is larger than I. Is j larger than I? Is 1 larger than 1? No. So we increase j by 1 from 1 to 2. Now I is equal to 1 and j is equal to 2. Is 2 larger than 1? Yes. So we now write down this term. And as I've told you before, I always take the 2 inside here. 2 times W1 times W2 times rho 1, 2 times sigma 1 times sigma 2. Okay, we've done that. Now we increase j to 3. Is 3 larger than 1? Yes. So again, we write down this term for the respective I and j. Okay, now j went from 1 to 3. 3 is equal to n, the number of assets. So what happens now? We increase I by 1 from 1 to 2 and start with j being 1 again. So now I is 2 and j is 1. Is 1 larger than 2? No. We increase j to 2. Is 2 larger than 2? No. We finally increase j to 3. Is 3 larger than 2? Yes. So now we enter this term again with the respective I and j. 2 times W2 times W3 times rho 2, 3 times sigma 2 times sigma 3. We are not finished yet because n, now j is now equal to n again. What we do now is we increase I by 1 from 2 to 3 and start with j being equal to 1. Is 1 larger than 3? No. So we don't write anything. Is 2 larger than 3? No, we don't write anything. And finally, is 3 larger than 3? No, we don't write anything. And now we're finished because both I and j have reached the upper limit of n, which in this example is equal to 3. And you can see, if we interpret the mathematical formula like this, we get exactly the same results as in our cookbook recipe. This would be step 1a, and this is step 1b. I want to present to you now an alternative formula, which is similar to the formula that we have just talked about for the portfolio variance, and I believe it is even more elegant than the first one, but if I correctly understand, it is not so widely used. The first part is the same as before. For every constituent we calculate wi squared times sigma I squared. It's a simple standard sum sign here, so that's the same like before. The second one differs the second term here differs somewhat from the formula I presented to you before, and you will realize that here we do not have any condition anymore. The first sum for I goes from 1 to n minus 1, and the second sum sign for j goes from I plus 1 to n. So if we start with I being equal to 1, then j starts with 1 plus 1, which is equal to 2. We enter the respective values for I being 1, j being 2. We then increase j by 1 to 3, and then enter the respective values. J is now equal to 3 to n, so we are finished here. So we increase now I by 1, and if to 2, so I is now 2, and if I is 2, then j starts with 2 plus 1 equal to 3. So we now have I is equal to 2 and j is equal to 3. We enter the respective values and we are finished, because I has reached the upper limit of n minus 1, 2. So I is equal to 2, j is equal to 3. We are finished. And you can see the formula is the same like before. This is step 1a and this is step 1b. The formula that I present to you here is now another alternative, the third formula that I present to you for the portfolio variance. It looks shorter in its mathematical notation than the two formulas I've presented to you, and it is probably not so useful if you do make the calculations with paper and pencil, but if you use programming and you do not have the possibility in your programming language to do any matrix operations, then this can be a useful alternative. So we say here that the portfolio variance is equal to this formula. We already understand what it means if we find two sum signs beside each other. And one thing that you should consider here is that the correlation II, the correlation of the same thing, like row 1, 1 or row 2, 2, is equal to 1. And you should also consider that row ij is the same like row ji. For example, the correlation between 1 and 2 is the same like the correlation between 2 and 1. We can write down the formula like this for the case of 3 assets, and it looks like this, 1 1 1 2 1 3 2 1 2 2 2 3 3 1 3 2 3 3. At first sight it looks a little bit different from the results that we got from our cookbook recipe, but when you have a closer look, then you see that these three terms here correspond to the first part of the formulas I've presented to you before. It's W1 squared, W1 times W1 is W1 squared, times 1, which we can neglect, times sigma 1 squared. Here we have W2 squared times sigma 2 squared. And here we have W3 squared times sigma 3 squared. Because rho 2, 2 and rho 3, 3 are equal to 1. Here we see, I is equal to 1 and j is equal to 2, and here I is equal to 2 and j is equal to 1. We've seen something like this before. Rho 1, 2 corresponds to rho 2, 1, so it's the same number. You see that this is the reason why we always had 2 times all possible combinations. And the same holds true for the next possible combination, which we find again 2 times. It's the combination 1, 3. And finally, for the third possible combination in our example of 3 assets, the combination 2, 3. So you will realize that this formula again yields the same results. Let me mention again, this can be a nice formula if you do programming and if you have in your programming environment no possibilities to use matrix algebra. Having mentioned matrix algebra, I shortly and without going into too much details want to present to you also the matrix formula for calculating portfolio volatility. You can find it here. The portfolio volatility is the square root of the transposed vector W, which contains the portfolio weights times the covariance matrix times again the weight vector. You can see the weight vector depicted here, and you can see here the covariance matrix. The covariance matrix is a matrix that contains in its diagonal the variances of the returns of the single portfolio constituents, and in the remainder you will find the covariances. Also for the expected portfolio return, there is a matrix formula which you can find here. It's W transpose times R, and R is a column vector containing the constituents' expected returns. Consider the following example, which I have conducted in Microsoft Excel, where I employed the matrix formula for the expected return of a portfolio and the volatility of this portfolio. What I have considered in this example is that we have an equally weighted portfolio consisting of 5 stocks, which means if we have 5 stocks that the respective portfolio weights are 20% for each stock, and the constituents are the 5 largest stocks that are traded on the Vienna stock exchange. How did I calculate the parameters? Well, I calculated the parameters based on the 36 most recent monthly return observations. So what you see here, these are values for monthly returns. The stocks that we have got are Erste Group, OMV, Raiffeisen Bank International, Verbund and voestalpine. Here are the respective volatilities. So you see Verbund had, based on historical returns, the highest expected return. Erste Group had the lowest volatility, and so on. And here you see the correlation matrix. Interestingly, you find a negative correlation. This is something that you do not observe too often between Erste Group and Verbund. And also the other correlation values in some cases are comparably low. For example, the OMV, Raiffeisen Bank International values are really low, and the same holds true for the Verbund correlation with OMV. And in some cases they are elevated, like for example Erste Group and Raiffeisen Bank International, but with a value of 54%, still considerably low, I would say. What you see here is a screenshot of my Excel sheet that contains all the relevant information that we need in order to calculate the expected return and the portfolio volatility. So here we have the vector W containing the weights. It's an equally weighted portfolio, so the weights are 20% for each of the constituents. Here we have a vector containing the expected returns, and this is the variance-covariance matrix. Recall that you can easily calculate the variance-covariance matrix on the basis of the constituents volatilities and the correlation matrix. The expected return for our equally weighted portfolio based on these estimates for the input parameters is 1.14% for monthly returns, and with a volatility of a bit more than 5%. I also calculated the Sharpe ratio. You recall the risk-adjusted performance measure. If we assume that the risk-free rate is equal to 0, then the Sharpe ratio is simply the expected return divided by the portfolio volatility. What I present here are some Microsoft Excel functions that are hopefully helpful when you tackle problems like the ones that we have just talked about. Recall that I estimated the parameters on the basis of 36 monthly observations. To estimate the vector of expected returns, respectively the expected return for every single constituent, I use the arithmetic mean. The Excel function to calculate this is average, and here in range you simply choose the 36 return observations. As for the volatility for every single stock, I used this function here. The volatility is estimated as the sample standard deviation of the 36 return observations. This is the formula for the correlation. And if you want to use the matrix formula, you also need the covariance, and this is the formula for the sample covariance. That's in range 1 you enter the 36 observations of stock 1, and in range 2 you enter the 36 monthly return observations of stock 2. If you use a language setting that is German, then you have to use in Microsoft Excel different names for the functions. The German version functions are displayed here. In Microsoft Excel, it's also possible to do matrix algebra. It's not very comfortable, but it is possible. And there are two operations that we need for our problem setting. The first is the matrix multiplication, and the second is the matrix transpose. For matrix multiplication, use the function mmult, like matrix multiplication. The first argument is the first matrix, the second argument is the second matrix. And for the matrix transpose, simply type transpose and then enter the range of the matrix that you want to transpose. And now here there's one important notice. If you want to enter matrix formulas in Excel, then it's not enough to simply hit the enter key, but what you must do is you must hold the control key and the shift key and then press enter. So here you can see how we can calculate our matrix formulas in Microsoft Excel. The first matrix formula that I presented to you was the one for the expected return. It's W transpose times R, where R is a vector of the expected returns. What you would have to type in Microsoft Excel is mmult. So you want to multiply two matrices. Which two matrices do you want to multiply? You want to multiply W transposed. So you have to write transpose and then enter here W, which is the range of your weight vector, comma, R, the range of your expected returns column vector. And then hold the control key, hold the shift key, and then hit the enter key. As for portfolio volatility, things get even a bit more complicated because the mmult function in Excel can only multiply two matrices at a time. So let us consider this matrix formula here. Let's maybe start with the most easy thing, the square root. The square root I have defined here. I calculate the variance and then take it to the power of 0.5, respectively 1/2, which is the square root. And what we find here is the Excel code for the variance, the thing that we find here under the square root. We want to multiply the transposed vector W, this is this guy, and we cannot multiply 3 matrices in a row, and because of this we have to write it like this. We multiply this guy here, W transposed, with a matrix multiplication, which is sigma and W, these guys here, multiplied. Again, you have to hold the control key, hold the shift key, and then press the enter key, and then it's going to work in Microsoft Excel. Here you can see the Excel sheet that I used to calculate the expected portfolio return and the portfolio volatility, and additionally the risk-adjusted performance measure Sharpe ratio using matrix algebra. What you find in this range is the vector of weights. We consider an equally weighted portfolio, so the weights are 20% for each of the 5 assets. Here you can see the expected return calculated on the basis of 36 monthly returns. So we're talking about monthly returns here for each of the 5 respective stocks. And this is the covariance matrix, where I calculated on the basis again of 36 observations the covariances between the different assets. Here you see the matrix formula for the expected portfolio return implemented in Microsoft Excel. So what we do is we multiply the transpose of the W vector with the vector of expected returns, and when we want to enter this we must press the control key, the shift key, hold them, and then press the enter key. You can here see that if you have got these curly braces, then Excel tells you that it has understood that this is a matrix operation. So if you see these curly braces, which you do not have to enter, simply hold the control key, the shift key, and press the enter key, you see these curly braces will appear here. As for the portfolio volatility, we multiply the transpose of the weight vector with, and then again we have to use mmult because Excel can only multiply 2 matrices at a time. Multiply the transpose of this guy with the covariance matrix multiplied with again the weight vector, and then take the square root. And this is the Sharpe ratio, 1.14% divided by 506%. If we assume that the risk-free rate is 0, then the Sharpe ratio is 0.225. Like before in this video, I have conducted some optimization procedures using Excel solver to calculate the minimum variance portfolio and the market portfolio. You find here the weights and the results for our initial problem setting, and here you find the results for the minimum variance portfolio. You see this portfolio is not anymore equally weighted. It is not invested in voestalpine, and it is heavily invested in Erste Group and Verbund, and also OMV, and a little bit in Raiffeisen Bank International. The resulting summarizing measures for the minimum variance portfolio are an expected return of 1.71 with a volatility of 4.59. You can see this results in a higher Sharpe ratio than the Sharpe ratio for our equally weighted portfolio. And what is also very interesting, it shows us that the initial equally weighted portfolio is not efficient in the sense of modern portfolio theory, because if we assume that our parameters are correct and that the models are correct, then a rational investor would not invest into this equally weighted portfolio. Why? Because the expected return of the equally weighted portfolio is less than that of the minimum variance portfolio, while the risk is higher. I've also calculated the weights and summarizing measures for the market portfolio. The market portfolio maximizes the Sharpe ratio on the basis of the input parameters. So by definition, the Sharpe ratio obtained for the market portfolio is higher than the ones of the equally weighted portfolio and the minimum variance portfolio. It has an expected return of 3.86% and a standard deviation of 6.89%, which is higher than the risk of the other two portfolios, but the risk-return relationship seems better. What you can see here too is that we have a short position in voestalpine, so the sum of the weights still is equal to 1, but we have a short position in voestalpine. We borrow these stocks, sell them, and invest them into the other four assets. And you see here in the market portfolio, obviously, the Verbund share has got a very high weight. At the end of this video, I want to very shortly present another software than Microsoft Excel to you. The software is called R. It's a statistical software. It's an open source software that is widely used in academia and more in practice. You can download it for free, and it is very efficient to solve questions like the ones that we addressed in this video. I just want to give you a short impression of this software R. because going into details would go beyond the scope of this video. It's an open source software. You can download it for free. You can download it here, or you simply Google R software install. What I did in this code, I loaded returns, estimated expected returns on the basis of the data that I loaded, and the data that I loaded was 36 monthly observations of the 5 stocks that we just discussed. I calculated the covariance matrix like this, and then I said the weight matrix weight vector is a matrix with one column which defines it as a vector and 5 rows, and enters 0.2. The respective values are always 0.2. I then calculated the expected portfolio return as the W transpose times the expected return, and I calculated the portfolio volatility as the square root of W transpose times the covariance matrix times W. In the R program, it looks like this. I execute the pre-written code in the R console, which you can see here. So this is our code for the video that we are just watching, and I first load the data. These are the 36 return observations for the 5 stocks. Then I define the vector of expected returns, which I call ER. I define the covariance matrix, which I call sigma, and I also define the weight vector, a vector with 1 column and 5 rows and a 20% weight for each of the 5 assets. I then calculate the expected return of the portfolio. This is W transpose times ER. This is what we use in R for matrix multiplication. So it's W transpose times the vector of the expected returns. The result is roughly 1.14%. And I also calculate the portfolio volatility, which is 5.06%. The volatility of portfolio is W transpose times sigma times W, and then I take the square root. This was a comparably long video on portfolio volatility. I hope you enjoyed watching, and I hope that it was a little bit helpful for you. Thank you very much. Best wishes and goodbye.